Another application of the ideal gas law is its application to gas mixtures. Since most gases that we deal with are mixtures, this understanding is very important. Now imagine a container that contains different gases shown by different colors. Let's say our red gases are A molecules. The blue molecules represent, let's say, B. And the green molecules, let's say they represent gas C. Each gas exerts some pressure, and we can actually give a name to that pressure, the pressure exerted by a gas itself, a particular gas in a mixture. We call this partial pressure. So gas C will exert a pressure. We're going to call that partial pressure P sub C. B will exert its own pressure, and it'll be partial pressure of B. And A will also exert its own pressure. We're going to call it partial pressure of A. And the total pressure in the system is the sum of all, which brings us to Dalton's law of partial pressures. The total pressure in a container of a mixture of gases is equal to the sum of the partial pressures of all the gases. The partial pressure of a gas depends on its number of moles. If you recall the ideal gas law, PV equals nRT, gases in the same container have the same volume, are at the same temperature, so pressure is directly proportional to number of moles. So which of these gases, red gas A, the blue gas B, or the green gas C, has the highest pressure? Well, which one of them have the highest number of moles? Well, let's count the atoms of each, or molecules of each. 1, 2, 3, 4, 5, 6, 7. We got 7 green, or molecules of C. Counting blue, we have 1, 2, 3, 4 of them. And counting red, we have 1, 2, 3, 4, 5 of them. So which of these gases have the highest number of molecules? Molecule C. So therefore the gas with the highest partial pressure is gas C. Which one has the lowest partial pressure? Well, the one with the fewest molecules of gas, which is the blue gas B. In a gas mixture, each gas exerts its own pressure as if it were the only gas in the mixture. For example, if you have a container that has oxygen at 159 millimeter mercury and nitrogen in an identical size container at the same temperature with a pressure of 593 millimeters mercury, if you mix these two gases, put in the same container, the total pressure will be 159 plus 593, totaling 752 millimeters mercury. Each gas is continuing to exert the pressure it did without the presence of the other one. It is independent of the other gas. You can therefore treat the gas mixture as if it's one gas. We can write P total is equal to, or P total times volume is equal to N total times RT. We can do that because pressure is proportional to the number of moles only, independent of the type of gas. But you can also write the ideal gas law for each gas independently, A being one of the gases, for example. Partial pressure of A times volume is equal to number of moles of A times RT. So depending on the case, we can use the ideal gas law for the entire mixture or just for one of the gases. Here we have a worked example. We have a 1 liter vessel that contains 0.215 moles of N2 gas and 0.0118 moles of hydrogen gas. The temperature is given to us. The question is, determine the partial pressure of each component and the total pressure in the vessel. The partial pressure of each gas can be calculated using the ideal gas law written for that specific gas. So partial pressure of nitrogen is equal to, basically calculated from number of moles of nitrogen, RT over V. When the values are plugged in, partial pressure is calculated 5.27 atmosphere. Similarly, partial pressure of hydrogen is calculated by using the number of moles of hydrogen only in the ideal gas law, applying it to only hydrogen, and gives us 0.289 atmospheres. These are the partial pressures of nitrogen and hydrogen, respectively. The total pressure, according to Dalton's law of partial pressures, is equal to the sum of the partial pressures. That comes out to be 5.56 atmospheres. Now, if you were only interested in the total pressure, you could have first calculated the total number of moles by adding the given number of moles to find the total, and then using the ideal gas law for the entire mixture, using the total number of moles, nRT over V, it will give us also 5.56 atmosphere directly. So you can apply the ideal gas law individually or to the total of the mixture. The composition, or the relative amounts of the components in a mixture, can be given using mole fractions. Mole fractions are just mole ratios for a component I of the mixture, the capital Xi being the mole fraction, is equal to number of moles of the component divided by total number of moles. There are a couple things to remember about mole fraction. The mole fraction of a mixture component is always less than 1. The sum of the mole fractions of all components is always equal to 1 exactly. And mole fractions are dimensionless. There's no unit to them. This is one step short of calculating mole percent. If you had multiplied fraction by percent, by 100, you would get mole percent. But we leave it as mole fraction. Remember, the mole fraction is the ratio of the moles of a component to the moles of the total. And because pressure is directly proportional to number of moles, you can also calculate the mole fraction using the partial pressure of the component divided by total pressure. This allows us to come up with an expression to calculate the partial pressure of the component, I, by multiplying its mole fraction with its partial pressure. As an example, let's calculate the mole fraction from given pressure data. We're given the partial pressure of all the gases in a person's lungs: nitrogen, oxygen, carbon dioxide, and water. Each has its own partial pressure. Because we're given pressures, the mole fraction of carbon dioxide can be calculated using the partial pressure of carbon dioxide divided by total pressure. The total pressure is the sum of all these pressures. If you add them up, it will give you 760 millimeters mercury. And we know the mole partial pressure of carbon dioxide, so we can directly plug into this equation. Carbon dioxide has a partial pressure of 40 millimeters mercury, and the total pressure is 760 millimeters mercury. The pressure units will of course cancel, and it will result in a dimensionless mole fraction. For this problem, it is equal to 0.0526. This is the mole fraction of carbon dioxide. Let's do a conceptual question now. Now imagine we have a flask. Let's draw that flask like a box with hydrogen gas. And then to this gas, we then introduce 3 moles of argon gas, same number of moles. I'm going to draw also 5 molecules. So here's the question. Blue being helium, red being hydrogen. What happens to the pressure of the hydrogen gas after the introduction of argon? Well, remember, gases exhibit or have partial pressures independent of the presence of other gases. So, partial pressure of hydrogen doesn't change. How do you compare the pressures of argon and hydrogen? That means argon partial pressure versus hydrogen partial pressure. Well, remember, for gases in the same container, pressure is directly proportional to number of moles. Because their number of moles are the same, their partial pressures are also the same. The number of moles of argon and hydrogen are equal to each other. How about the total pressure? Well, the total pressure is equal to argon pressure and hydrogen pressure.